Andarki namaskaram. Good afternoon all. Welcome you all to the teleconference conducted by Department of Chemistry, Dr. B.R. Ambedkar Open University. Today we are going to discuss about the topic Stereoisomerism of carbon compounds. It belongs to BSc second year semester 4. It is also covered some fundamentals of organic chemistry pertaining to MSc first year. To explain this program, we have subject experts Dr. J. Mohan Babu, Assistant Professor, Usmania University, and D. Koteswararao, Assistant Professor, Department of Chemistry, Dr. B.R. Ambedkar Open University. With us in our studio. This program will be 60 minutes. In first 40 minutes, topic will be explained. Next 20 minutes, we will be taking question regarding subject and will be explained. If you have any questions, post your question in chat box or call to 040-23680-456. 040-23680-456. For interaction with us resource persons. Today's topic is stereoisomerism of carbon compounds. Dear learners, before going to the topic, we need to familiar about some fundamental aspects of isomerism. We know the carbon exhibits its valency is 4. Due to its valency, carbon exists in sp3, sp2 and sp hybridization. sp hybrid carbon is linear and sp2 hybrid carbons are planar. But in the case of sp3 carbon is occupied in 3D space due to its geometrical differences and different arrangements of carbon compound exhibits isomerism and molecules are called isomers. These isomers are again classified as constitutional isomers and stereoisomers. The molecules are chain, positional, functional and tautomers. Ring chain isomers are called constitutional isomers. Now I am asking Koteswararao, please explain what is stereoisomerism, how these are classified.
Yeah. As madam said, carbon is having a 4 valency. 4 valency means it is capable of forming 4 bonds. Due to this advantage, carbon can form several kinds of compounds. That is the reason in the organic chemistry we will see billions of compounds in its library. Therefore, it is have greater importance to understand the structural properties for the application purpose. Here the carbon can gives or can shows 3 kinds of hybridization. One is sp3 and another one is sp2 and another one is sp. sp hybrid molecules are the linear. For example, alkynes are the linear molecules. At the same time, sp2 hybrid molecules are the planar molecule. For example, alkenes. Alkenes are the 2-dimensional molecules. These 2-dimensional molecules are the planar molecules. Now, today's our topic about the stereochemistry. The stereochemistry, especially for the molecules which is generated by the fully saturated compounds, that is the sp3 carbon involved compounds and sp2 carbon involved compounds. Firstly, we coming to the sp3 carbon involved compounds. These are the saturated compounds. In that saturated compounds, carbons are attached with 4 groups or atoms around the carbon. These atoms or groups are arranged in the 3-dimensional space. Now here the term stereo means space. The arrangement of groups or atoms in the space around the carbon is called stereochemistry. If the compounds of carbon shows the isomerism due to the spatial arrangement are called stereoisomers. Before going to the topic, the carbon compounds are generally shown isomerism due to the difference in the property, however they are having the same molecular formula, right. Based on that, these isomers can be classified into constitutional isomers and stereoisomers. Here I am going to show a flow chart for the isomerism. According to this flow chart, isomers are classified into structural, were also called as constitutional isomers, and another case is stereoisomers. First, you come into the constitutional isomers. Here we can see 6 types of constitutional isomerism is there. In that, the first one is chain isomerism. Chain isomerism is due to the compounds may be a straight chain or a branched chain. For example, you take N-butane and isobutane. This N-butane is the straight chain and isobutane is the branched structure. Both are having the same molecular formula but difference in their physical and chemical properties. Okay, these are called as chain isomers. Next, ring chain isomers. The ring chain isomers, when we are comparing the two compounds which are having the same molecular formula, but one of them is exist in the form of a acyclic form and another one is in the form of cyclic form. For example, 1-butene is existing the ring chain isomerism with the cyclobutane. Also, 2-butene is also have the ring chain isomerism with cyclobutane. Next, positional isomers. Here we are taking the functional group as the reference and its position. If you take 1-butanol and 2-butanol, here the 1-butanol is having the hydroxy group at first position and in the 2-butanol hydroxy group at second position. These are called as positional isomers. That means a functional group, it is only difference in the molecule is its position. Those isomers are called as positional isomers. Another example, if you take the aromatic derivatives, if you take the anilines or nitrobenzenes, the toluene is the compound. In the toluene, amino group is substituted at second position, that is the orthotoluene. It is the third position, it is the metatoluene, and at fourth position, that is called paratoluene. If you see that amino groups are changing their positions, due to the changing of their positions, those are known as positional isomers. These three are existing as a positional isomers. And functional isomers. Functional isomers means one of the atom or a group existing in the group in different functional nature. For example, hydroxy, that hydroxy compound is having oxygen as element in its molecular formula. That is maybe exist in the form of alcohols or in the form of ether. However, they are having the same molecular formula. These are known as functional isomers. Here I am going to give you one example. Ethanol shows the isomerism with the dimethyl ether. The dimethyl ether is the ether functional group. In the alcohol, that is the ethyl alcohol, is the just hydroxy compound. Similarly, if you take the acetic acid, very familiar compound, it is the carboxylic acid functional nature. Its isomer is methyl formate. It is the ester. We can see that ester and acid are isomeric in nature. That is functional group isomerism. Next, metamers. These metamers are differentiated by the alkyl groups around the functional group. That means different alkyl groups are attached to the functional group in different manner. If you take here the methyl and ethyl group is attached to the ether. For example, diethyl ether is showing the metamerism with the methyl methyl propyl ether. That means in the first case, two ethyl groups are attached to the oxygen, that shows the diethyl ether. In the second case, the methyl group and propyl group is attached to the oxygen, that is, it is showing the metamerism. These are known as metamers. Next, tautomerism, or the isomers are called as tautomers. If you take ketone, if you take acetone, it is having alpha hydrogens at the alpha carbon. This hydrogen is undergoing exchange between the alpha carbon and oxygen. It will be exist in the form of keto or keto and enol form at room temperature. It is the dynamic exchange. Due to its dynamic exchange, equal amounts of enol and keto forms are observed in the acetone solvent. This is called as tautomerism, and namely keto-enol tautomerism. Similarly, if you take enamine, the hydrogen is exchanged from nitrogen to the second position, that leads to the formation of enamine forms the imine due to the exchange of hydrogen from the nitrogen to third position of carbon, right? Therefore, these two molecules are exist as a imine tautomerism. These two are the tautomers, and this tautomerism is called as imine tautomerism, right? Next, coming to all these, first thing, chain isomers, ring chain isomers, and metamers, tautomers, positional isomers, and functional group isomers are called as constitutional isomers. Okay, in the other direction, other way, the carbon compounds are existing in the other form of isomers are called stereoisomers. What are the stereoisomers? Previously, the constitutional isomers and stereoisomers are differentiated by the only differ in the bond connectivity. If it is having different bond connectivity, those are called as constitutional isomers. A bond order or bond connectivity is same, those are called as stereoisomers. These stereoisomers can be classified in three ways. No single classification will not fulfill the full classification. These three classifications are mutually complete the total classification of stereoisomers classification. These are one another are complementary to each other. Okay, in that first classification is called Mislow classification. This is based on the bond connectivity and geometry. Bond connectivity and geometry. Stereoisomers, if you take two isomers are there, when you compare them, when you are comparing, these isomers are non-superimposable mirror images. Here the term non-superimposability. Superimposability means if you take two papers, keep one and other, both two papers are superimposed to each other. That is called superimposability. Now you take the two hands of human, keep aside and keep one over the other. Every finger will not occupy the other hand. This is called non-superimposability. Non-superimposability. Similarly, here the stereoisomers are also showing the non-superimposability. Non-superimposable mirror images are called as enantiomers. These enantiomers are optically active. And second type, stereoisomers are other type. Those are non-mirror images. Those are not a mirror images at all. Those are called as diastereomers. Here the enantiomers are non-superimposable mirror images, and diastereomers are not a mirror image. Those two are stereoisomers. They are having the same molecular formula, same bond order or bond connectivity, but they are not a mirror images. Those are called as diastereomers. Again, these diastereomers are classified into optically active diastereomers, and the second one is the geometrical isomers. In the case of optical active, those are having a chiral center. They are showing the optically active in nature. Those are called optically active diastereomers. However, some molecules are having the chiral center. They are existing as a non-optically active or optically inactive. Those are called mesoisomers. In the case of geometrical isomers, these geometrical isomers are stereoisomers, however they are optically active mirror images, not a mirror images. And other case geometrical isomers, the arrangements of groups or atoms around a double bond which is between the two carbons and carbon nitrogen are called as geometrical isomers. Geometrical isomers. Further, stereoisomers are classified based on the energy barrier. Energy barrier. Based on the energy barrier, stereoisomers are comparing when they are interconvertible at room temperature or not. That is the comparison. Right, okay. When the stereoisomers are interconvertible at room temperature, those are known as conformational stereoisomers. The stereoisomers are not able to interconvertible at room temperature are known as configurational stereoisomers. What is the energy involved in this interconversion? Why they are interconverted at room temperature and some of are not? That is due to there is a possibility between the carbon-carbon rotation, carbon-carbon bond rotation, that is responsible for the interconversion. This rotation requires the less than 60 kilojoules per mole energy. This energy is provided at room temperature, therefore they can rapidly undergo the rotation and rapidly convert from one stereoisomer to another stereoisomer. Due to that reason, these isomers are called as conformational stereoisomers. Next, coming to the configurational stereoisomers. The configurational stereoisomers, they are not at all interconvertible at room temperature. These compounds or these stereoisomers are associated with the bond cleavage and bond formation for the interconversion. For bond cleavage and bond formation, it requires more than 100 kilojoules per mole. That means the average in between 100 kilojoules moles to 400 kilojoules per mole is required to cleave a bond and to form a bond. Therefore, that energy is not available at room temperature. If you provide any external energy due to the heating or photochemical irradiation, those are participating in the bond cleavage and bond formation, therefore they can be interconvertible. Those kind of stereoisomers are called as configurational stereoisomers. Again, these conformational stereoisomers and configurational stereoisomers are classified based on the internal energy. The internal energy is same. Those stereoisomers are called as enantiomers. Same internal energy with conformational isomers are known as conformational enantiomers. These conformational enantiomers are having the same internal energy.
Okay, Koteswararao. Next, I request Dr. J. Mohan Babu, what is optical activity? How it is determined? Explain this topic.
Yeah, as Koteswararao sir said, with the enantiomers and diastereomers, so where the isomers which are non-superimposable mirror images are called the enantiomers, and the non-superimposable non-mirror images are called the diastereomers. And generally this isomerism, the stereoisomerism, will be obtained by when these are having the chirality here. So chirality in the sense where the carbon, the central carbon atom, when it is surrounded with the 4 different groups. For example, the central carbon atom is attached with the one hydrogen, another tritium, another methyl, another ethyl. So you see around that carbon, you can see the 4 different groups are the atoms here. So the central carbon atom becomes a chiral carbon. We said it is a chiral carbon. So this chiral carbon having a special case of the special phenomena in the organic chemistry, where the chiral compound able to rotate the plane polarized light. So the compounds, the chiral compounds which are able to rotate the plane polarized light is called the optically active compounds. And basically what is the plane polarized light here? So how do you differentiate the plane polarized light with the normal light here? So generally the normal light and the plane polarized light both are different here, where the normal light is it is multi-directional light and it emerges in the multiple planes, and it is a polychromatic light. Polychromatic means it is having variety of wavelengths here, variety of lights, like you see the rays like in the EMR. Okay, so where the normal light, it is consisting of two components like electromagnetic radiation and electric field here. Okay, so these two are the perpendicular to each other, and when we see in the EMR graph, so we have the variety of radiations like X-ray, gamma ray and lambda rays, and so all these are the IR rays, UV visible rays. So all these are different rays which is composed with this particular EMR here, and we can see the variety of wavelengths in this particular EMR. So your normal light is consisting all these rays here, but your PPL, plane polarized light, does not have all these composition here. It is having only single wavelength here, and it is having only single radiation. So how to convert this particular plane polarized light here from the normal light? So generally this particular monochromatic light, right, monochromatic light will be obtained by passing from a special light here sources, from a special light sourse like sodium lamp. If you pass a normal light through this sodium lamp here, so it generates a monochromatic light, and this monochromatic light, when it is passing through the nickel prism, so this monochromatic light converts into plane polarized light here. So you see the plane polarized light is having only single direction, only one direction, unidirection here, where you can compare with the normal lights. So if you see the lights, you see in this particular instrument, you can see in the second one, right, this is the normal light beam here, and you see the first one is a light source, that is a sodium lamp, and in the second component is your normal light beam. So you can observe the variety of the directions here. It is in multiple directions, right? So they randomly arrange the rays, right? When this particular normal light is passing through that particular nickel prism, so that particular light is polarized into one direction. The multiple directions converts into single direction, and this single direction will be obtained by the passing through this particular polarizer here, right? So this kind of rotation of this plane polarized light by the chiral compound is called the optical activity. So optical activity only possible for the chiral compounds only, and this particular optical activity will be measured by the polarimeter, and this polarimeter is having some components here, where it is having the light source, and that is particular the polarizer and the analyzer and the sample tube. So where the sample tube is used for the holding of the sample solution here, and the finally it is having the analyzer and that observer here. So these are the variety of the different kinds of the components having the polarimeter, and your optical rotation is obtained by, means measured by the polarimeter. And in the polarimeter, how to measure the optical activity or the optical rotation here? So optical rotation is measured by this particular polarimeter, and this polarimeter is arranged in a way that where the source, the light source and the polarizer and the sample tube and the analyzer. So all these are arranged in a parallel manner here, and all these are in a one line here. So the particular observer can able to see the light, PPL light, plane polarized light. So from which direction it is going to rotated here. So when before going to analyze of the your sample, so first you have to check that whether this particular solution is having the optical activity or not, and you have to arrange that part. You calibrate the degree of rotation, for the maximum. So you can set the maximum angle of the rotation by checking with the empty tube, or you can check with the water. So when you fill this sample tube with water, generally the water is not a chiral nature here. So it is showing the maximum, the optical degrees of the rotation here, right. So then you fill that particular sample tube with the your solution, means your compound which is undergoing the investigation. So then you check that, right. So you check that with this particular compound, and when you are observing, if that plane polarized light is rotated towards the left side, then we can say it is a lever rotatory compound, right. So generally your PPL, it is a unidirectional light here. So it is arranged in a maximum degree of rotation. Then we will check with the sample, we will fill the sample in this particular polarimeter. Then we will see that from means this compound rotating the light from which direction, right. If it is rotating the light to the left side here, so we call it is a lever rotatory, and we will shown with the minus charge here, means minus symbol, right. And if the PPL, plane polarized light, is rotated towards the right side, then we call it is a dextrorotatory compound, and we will denoted with the plus symbol here, right. So here is a R and S. Okay, so here the R and S, these are the configurational nomenclature. It is not related to the angle of rotation in the optical activity here, and whatever the symbols we use after the configurational nomenclature like R and S, so that is indicating your optical rotation here. And generally this optical rotation, it is shown by a special word, that is a specific rotation here. So generally the specific rotation, nothing but where the angle of rotation done by the optically active compound at a special condition is called the specific rotation. And here the special condition generally will take the temperature, and will take the wavelength of the particular light source here, and will take the solvent, and will consider the tube length also. Generally the tube length is taken in the decimeter here, right. So for example, any compound which is underwent the examination of its specific rotation at 25 degrees temperature, right. So it is showing that minus 66 degrees angle rotation here. Then that means the particular compound is having the specific rotation at 25 degrees and at a wavelength of 586, okay, it is 586 lambda wavelength, and it is minus 66 means where it is a lever rotatory compound, right. So in this way we can find out the specific rotation of that particular compound. And while we are reporting the specific rotation, generally one should mention the temperature and the wavelength of the radiation and the solvent which is we are using, and the length of the sample tube, right. So sample tube it is various, right. So sometimes we use the diameter is sometimes we are using the large diameter, and sometimes we take the smaller one. So that is also one of the important thing considerable when we are measuring the specific rotation of the particular compound. And generally the specific rotation calculation is done by using this particular formula. So we can see the formula, like it is a lambda T and that is a lambda sorry, alpha, right. So it is alpha T and lambda equal to alpha LC. So here the lambda, which is shown in the mentioned in the bracket, and suffix is T, and right below we are mentioning with the lambda. So lambda indicating the wavelength of particular light, and upon we are shown with the T. So T is the temperature. So condition must be mentioned, and the alpha, it is the angle of rotation, how much rotation is done by the optically active compound, right, that should be mentioned. Then by LC, L is the length of the tube, okay, the length of the tube here, and C is the concentration of the solution, right. The concentration also plays an important role for the calculation of your specific rotation. So this is the formula which is used to calculate the optical activity of the particular compound and to find out the specific rotation here.
Okay, thank you, Mohan. Now I request Koteswararao sir, what are asymmetric and disymmetric carbons? Explain about different molecules with asymmetric and disymmetric centers.
Yes, this asymmetric and dissymmetric centers purely depends on the chirality of the molecule, right. What is chiral molecule? The chiral molecule, the carbon, or not only carbon, nitrogen, sulfur, these are also showing the chirality, but we are discussing about the carbon only. The carbon which is attached to 4 different groups or atoms. Okay, if it is a single centered chiral molecule, all these molecules are asymmetric. Why we are call it as asymmetric? Except identical symmetry, there is no other symmetry elements present in it. Due to that reason, these molecules are called as asymmetric molecules. For example, here I am showing D-glyceraldehyde and L-glyceraldehyde. These molecules are asymmetric in nature. Similarly, 2-hydroxypropionic acid, plus and minus are DL isomers. These are also called as asymmetric compounds, asymmetric stereoisomers or asymmetric enantiomers. Okay. Now, what is dissymmetric? Previously we called it as the molecule which possesses the only identical symmetry, that is C1 is present, those molecules are called asymmetric. And the next class of molecules we call it as dissymmetric. When we call it as dissymmetric, the molecule, here also the molecules are chiral molecules or optically active molecules, but they possess C2, C3 and C6 and D2 and D3 symmetry elements. Whenever these are having more than one symmetry elements, therefore the symmetry is more when we compare to the C1. More number of symmetry elements are there. Due to that reason, these compounds are called as dissymmetric molecules. In the dissymmetric molecules, we consider D-tartaric acid. This D-tartaric acid having a C2 axis. Previously we called it as C1 symmetry element is there or C1 point group is there. That point group containing molecules is called asymmetric. But here this D-tartaric acid is having C2 point group or C2 axis. Therefore, this molecule is called a dissymmetric molecule. Similarly, it is also having C2 axis. This is called alene derivative 1,3 dichloroalene. This is also dissymmetric molecules. Further, if we consider molecules with more than one chiral center, that means the compound may containing 2 or more chiral centers, these molecules are further classified into molecules with more chiral center in symmetrical structure with symmetrical structure and unsymmetrical structure, or symmetrically substituted structure, unsymmetrically substituted structure. First we coming to the molecule containing one chiral center. Here I already discussed the molecule containing 2 asymmetric carbon atoms. In this case, molecule with 2 similar asymmetric carbons, two similar asymmetric carbon. For example, you take the tartaric acid. In this tartaric acid, two chiral centers are there. These two chiral centers are containing tartaric acid are uniformly distributed COOH, 2COOH and OH. Okay, it exhibits stereoisomerism and forms 2 to the power of n number of stereoisomers. In the 2 to the power of n minus 1 plus 2 to the power of n minus 2 by 2 stereoisomers. That means in that 2 to the power of n minus 1 isomers are the active isomers, 2 to the power of n minus 2 by 2 isomers are meso or achiral isomers, stereoisomers. Similarly, if the molecules with more than or odd number, here tartaric acid is having the even number, 2 carbons are there. If the tartaric and other than tartaric acid which is having 3 or 5 or 7 odd number of chiral centers are there, those kind of molecules are showing 2 to the power of n minus 1 stereoisomers. In the 2 to the power of n minus 1, 2 to the power of n minus 1 by 2 stereoisomers are active isomers, that is chiral isomers. 2 to the power of n minus 1 by 2 isomers are achiral isomers. Okay, when you coming to the unsymmetrical asymmetric carbon atoms, molecules with containing more than one chiral center. For example, we take butyric acid, 2,3-dihydroxy butyric acid. In such case, the molecule showing 2 to the power of n number of stereoisomers. In the 2 to the power of n stereoisomers, 2 to the power of n minus 1 isomers are active isomers, and 2 to the power of n minus 1 isomers are achiral or mesoisomers. Okay, this is about the asymmetric and dissymmetric molecules.
And now I request Mohan Babu, what is a racemic mixture? How they are prepared and separated to individual and pure compounds?
Yeah. So as we discussed the optical activity earlier, so generally here the compounds, right, the chiral compounds, which chiral compound are showing the optical activity here, and generally when a particular compound, right, the chiral compounds are having with two different configurations like R and S. Okay, so these two different configurations, so with equal proportion, with equal quantities here, means 50% of R isomer and 50% of your S isomer. So when these two isomers are have formed together, then we call these are the racemic mixture here. So racemic mixture nothing but the equimolar isomers present in a same sample is called the racemic mixture. And generally this racemic mixture is formed during the chemical reaction when the attack of the reagent from the two direction in equal proportion here. For example, if any you take any carbocation, you take tertiary carbocation here. So in the SN1 reaction, so you are aware of the SN1 reaction. So in the SN1 reaction, when that particular the OH minus nucleophile is attacking from the front side, right? So you will get the retention of the configuration, and when it is attacking from the back side, so we will get the inversion of the configuration, right? So where the except the OH group which is out means which is coming from the outside, right? So rest all position of the atoms is same, but only they differs in the position of the OH groups here. And if you see the rotation of these means these two compounds, one becomes plus, another becomes minus, means one compound configuration is going to R, another compound configuration is going to S here. So in that case, the rotation, optical rotation of the R configuration, right, it is cancelled by the optical rotation of the S configuration. So in such a case, the net result of the optical rotation is 0. Okay, so because the R configuration, for example, it is rotating to the plus 50 degrees angle of rotation, and your S configuration again it is doing the minus 50 degrees of the angle of rotation here. So this plus 50 and minus 50 both becomes cancelled each other, and the net result is the 0. So such compounds is called the, these are called the meso compound. We mentioned with the meso compound, and having these two isomers we call the racemic mixture here. Okay, so in this particular example we can explain about that. So this right, the phenyl derivative where the bromine is attacking from the front side, because here the phenyl carbocation, right, so the phenyl butyl carbocation, it is a planar one. So planar, it is having the equal proportion to attack the bromine ion from the, either it come from the front side of all the directions, because it is planar one, so it can approach from the any direction here. So we are getting the two isomers with 50% of the each one. So the optical rotation is going to cancel each other. So we call these are the racemic mixture here. And generally this racemic mixture, right, so can be separated by various method here, because the racemic mixture is not optically active compound, and this is not useful to the any some reactions here. So we can separate these isomers individually by using some methods here, right. So in that methods we have variety of methods are mentioned, and the separation of this isomer we call the resolution, and the resolution of this racemic mixture is done by different methods like mechanical method, chemical method, diastereomeric method, and enzymatic method. So these are the some approaches or the methods to separate the racemic mixture in the pure form here. First we will see the resolution of the racemic individual components from the racemic mixture by mechanical method or the by hand method here, right. So in the mechanical method generally it is applied by the Louis Pasteur in the 1848 year. So as per the Louis Pasteur, right, so he was observed that where the sodium ammonium tartarate, this compound, when it is crystallizes, so he found the formation of two different sizes of the molecules here, two different sizes of the molecules. So and these two molecules can be visible by the magnifying lens here, and we can identify the different shapes of the isomers, R isomer and the S isomer. So we can separate these two isomers individually, individually here. Okay, so this is the resolution method by mechanical method or the by hands sort out method here. But the difficulty with this particular method is generally the all the right, so all the compounds does not crystallizes frequently here, right, means they won't crystallizes rapidly. So that is one of the disadvantage of this mechanical method. And generally this mechanical method is applicable only for the solid state compounds. It is not applicable for the liquid solutions here. So this is also one of the disadvantages with this particular mechanical method. And the second method is the enzymatic method. So in the enzymatic method it is done the separation of the individual pure isomers by using the enzymes here, right. So generally here where the two isomers which is reacted with the enzyme by taking the enzyme, right. So we can separate the isomers. So what happens in this particular enzymatic method? So the enzyme will be destroys the one.
Hello.
Hello. Namaste, madam.
Namaste.
మేడం నా పేరు కృష్ణ. ఇది బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీలో నేను అడ్మిషన్ అనేది పొందాను. ఇప్పుడు ప్రతి సంవత్సరం అనేది ఇప్పుడు ఫస్ట్ ఇయర్ సెమ్స్ వచ్చి డిసెంబర్ నుంచి జనవరి మధ్యలో కండక్ట్ చేస్తారు. సెకండ్ సెమ్స్ వచ్చి ఇది ఏప్రిల్ టు మే మధ్యలో అనేది కండక్ట్ అనేది చేస్తారు. కానీ ఈ ఇయర్ లో మాత్రమైతే బిఆర్ అంబేద్కర్ యూనివర్సిటీ విశ్వవిద్యాలయం కేంద్రం వారు ఎందుకు ఇంకా అడ్మిషన్ యొక్క గడువు అనేది ఇంకా పెంపొందించడం వల్ల ఇప్పుడు చదువుకోవడానికి ప్రతి ఒక్క విద్యార్థి విద్యార్థులు కూడా చాలా ఇబ్బందికరంగా అవుతుంది సార్. ఎందుకంటే ఇప్పుడు టైమింగ్ అనేది కూడా ఎక్కువగా కూడా లేదు. ఇంకొకటి సార్,
yes, so in the biochemical method or the enzymatic method,
ఓన్లీ సబ్జెక్ట్ రిలేటెడ్ క్వశ్చన్స్ మాత్రమే తీసుకోవడం జరుగుతుందండి. ఏమైనా జనరల్ ఇష్యూస్ ఉంటే మీరు హెల్ప్ లైన్స్ గ్రేవియన్స్ సెంటర్ ఉంటుంది, దానికి ఫోన్ చేసి మాట్లాడండి దయచేసి ప్లీజ్. ఇది సబ్జెక్టుకి సంబంధించిన ప్రోగ్రామ్ కాబట్టి దీనికి సంబంధించిన మీకు ఏమన్నా డౌట్స్ ఉంటే అడగండి, మేము క్లారిఫై చేస్తాం.
so in the enzymatic method, so where among the two isomers, so one isomers will be digested by the enzyme here or destroyed by the enzyme, and another isomer is obtained in the pure form, right? So this method also having some disadvantage where we are getting only one isomer here. One isomer is going to destroyed, and another isomer is we are getting in the pure form here. So we are losing one isomer. So this is also one of the disadvantages of this method. Then we are having the another method where the diastereomeric method here. So and generally the frequently using method, and this is.
Hello, good afternoon.
చెప్పండి.
హలో చెప్పండి.
నమస్కారం మేడం.
నమస్తే
మేడం, ఇది ఇప్పుడు నాకు బిఎస్సిలో ఇప్పుడు
ఇవన్నీ కాదు, మీరు
ప్రాబ్లం అనేది
సబ్జెక్ట్
రిలేటెడ్. హలో,
మేడం,
ఇది ఓన్లీ సబ్జెక్ట్ సంబంధించిన క్వశ్చన్స్ అడగండి. ఇది లైవ్ టెలికాన్ఫరెన్స్ కెమిస్ట్రీ ఇది. అదే చెప్పండి మీ క్వశ్చన్.
కెమిస్ట్రీలోనే ప్రాబ్లం అనేది వచ్చింది మేడం. ఎట్లా అంటే ఇప్పుడు ఎగ్జామ్ టైంలో ఇప్పుడు ఇంటి దగ్గర ఉండి జరా
yes. So next in the dash,
okay,
yes, so in the diastereomeric method where this particular racemic mixture, right here the racemic mixture is interacted with the optically pure chiral compound here. Then this particular optically pure chiral compound will be reacts with the both isomers, both enantiomers here, and both will be gets formed the diastereomers here, right? And these the formed diastereomers, generally we know that the diastereomers are having the different properties here, right? They will shows the different chemical properties and the physical properties. So with this difference in the properties, so we can easily separate this particular enantiomers in the pure form, right? So if you see the reaction here in this right, you can see with this reaction here where this particular the tartaric acid, right, the tartaric acid when it is treated with the amine derivative chiral compound, right, and here the very important thing is where the outsider, okay, the outsider compound must be chiral and it must be optically pure, and the outsider compound which is treating to this enantiomers, it must be easily available and it must be stable to the reaction conditions here, okay. So here you can see in the equation where this particular the amine derivative when it is reacting with the both the isomers of tartaric acid, so it is converting into the acyl derivative here, and this both the acyl derivative further upon the hydrolysis, right, upon the hydrolysis both are going to separated as pure enantiomers here, right. So in this way we can separate the enantiomers, and one more method also available like the chromatographic method. So generally you know that the column chromatography where it is having the stationary phase and the diastereomers, after converting into diastereomers, so we can take both the isomers in the column chromatography and when we run in the solvent medium, so one isomer will get separated first, then the second will be get separated later. So by the difference of their properties, we can separate the individual pure enantiomers by this resolution technique here.
Okay, thank you, Mohan. Now, Koteswararao, explain what is configuration, how can we determine configuration of asymmetric and dissymmetric molecules?
Yes. As we discussed earlier about the stereo means space. In the molecule, we already said that groups or atoms are arranged around the carbon. Now, here the configuration indicates or a notation represents the exact positions of groups or atoms are attached to a carbon in the three-dimensional space is called as configuration. This configuration can be in two ways. First one is relative configuration and the second one is absolute configuration. In the relative configuration, here the name itself represents relative configuration. Relative means we are taking one reference, based on that where our compound is comparing with that and relate it, then we can decide the notation or configuration. That is called as relative configuration. These relative configurations are several types based on the compounds we are considered. Here the DL configuration is the relative configuration. Similarly, erythro-trio, endo, exo, cis, trans and syn and anti. These are called as relative configuration. Whenever we are coming to our chiral compounds or chiral stereoisomers, we consider DL configurational nomenclature. In the DL configurational nomenclature, whenever we are going to assign the notation in the form of a configuration, that is called nomenclature. That is the reason we call it as DL configurational nomenclature. In this DL configurational nomenclature, it is proposed by the Fischer and Rosnoff by taking the reference compound is glyceraldehyde. Here, whenever they are working, they are identified one compound. In that compound is glyceraldehyde. In that glyceraldehyde, hydroxy group is arranged at the right side, that is denoted as D-glyceraldehyde, and similarly its enantiomer mirror image is denoted as L-isomers. These two compounds are arbitrarily taken as a reference material for assigning the DL configurational nomenclature for the other compounds. But here the requirement is for assigning DL configurational nomenclature, molecule should be represented in a cross formula or a Fischer projection formula. In that Fischer projection formula, we are for example, if the compound is having only one chiral center, in that chiral center the functional group which is arranged, the reference functional group which is arranged at the right side, that compound chiral center is denoted as D configuration. At the same time, the reference functional group is arranged at the left side on the chiral center, that is denoted as L configuration. Okay. For example, some compounds are having more than one chiral compounds. In that case, that compound containing bottommost chiral center is taken as the reference. That reference, in that reference center, the functional group, the reference functional group is arranged to the right side, that is denoted as D configuration. If it is the left side, that is denoted as L configuration. For example, you take D glucose and L glucose. In the D glucose, from it is having the 4 chiral centers. In the bottommost chiral center, at that carbon, the OH is arranged at the right side, that is called as D glucose. If the OH is arranged to left side, that is denoted as L glucose. Most of the amino acids are showing L configuration. Naturally occurring amino acids are showing L configuration. Okay, most of the sugars, naturally occurring sugars, are showing D configuration. Okay, this is the reference nomenclature. We are taking the glyceraldehyde configuration as the reference configuration. It is comparing with the other compounds configuration, stereochemistry, then we can assign the configuration. Okay. Now absolute configuration, RS configuration. Here the RS configuration means R means rectus and S means sinistus. This is the R means right handed side or right handedness. S means sinistus, that is left handedness or left handed side. Okay. For assigning RS configuration, whatever the groups or atoms are attached to the carbon, 4 groups or atoms are attached to the carbon, we need to assign the priorities. We need to assign the priorities by following the CIP priority rules.
Hello. Hello.
Hello.
Hello.
Good afternoon, ma'am.
Good afternoon.
I'm a student from second semester, ma'am.
Okay. అడగండి, క్వశ్చన్ ఏంటో అడగండి.
అబౌట్ ద గ్లూకోజ్ లో పాసిబుల్ ఐసోమర్స్ గురించి ఎక్స్ప్లెయిన్ చేస్తాను.
ఏంటేంటి మళ్ళీ ఒకసారి అడగండి క్వశ్చన్స్.
గ్లూకోజ్ లో పాసిబుల్ ఐసోమర్స్ గురించి ఎక్స్ప్లెయిన్ చేస్తాను.
స్టీరియో ఐసోమర్స్.
ఓకే ఓకే, ప్రాబ్లం.
Yeah, in the glucose, yes.
ఎక్స్ప్లెయిన్ చేస్తున్నారు, మోహన్ సార్ ఎక్స్ప్లెయిన్ చేస్తున్నారు, వినండి.
ఓకే మ్యామ్, థ్యాంక్ యూ.
Yeah, so in the glucose, you can draw the possible isomers in the glucose by using the formula 2 power of n, right? So here the n equal to the number of chiral centers here. Okay, n equal to the number of chiral centers. Generally in the glucose, so generally glucose consists how many chiral centers here? There is a right, you can say it is 6 carbons. Okay, and you see 1 2 3 4. Okay, there are 4 chiral centers are there. So the 2 power 4 means how many isomers possible here? 2 power 4 means the 8 isomers are possible, isn't it? So 8 isomers. Among the 8 isomers, the 4 isomers are the D isomers, and the remaining 4 2 power 4 is 16, sorry.
16.
Yes, 2 power 4 is a 16. So 16 isomers are possible. Among these 16 isomers, the 8 isomers are the D isomers, and another 8 isomers are the L isomers. So you can calculate by using the 2 power n formula.
Okay. Right.
ఓకే, థ్యాంక్ యూ మోహన్.
Just simple. I'm adding CIP configuration, RS configuration nomenclature. Whenever we are giving to the priorities to the groups or atoms around the carbon, we need to follow the priority rules. These priority rules are CIP rules. We call it as Kohn-Ingold-Prelog rules. According to the Kohn-Ingold-Prelog rules, we have some 6 or 7 rules are there. By following the 6 or 7 rules, we need to assign the priorities as 1 2 3. Like similarly here one molecule is given. According to we are giving the priorities by following the CIP rules. Now 1 2 3 4. Okay, just connect the first to 3 priorities 1 2 3. If the connecting arrow is a circular, either it is a clockwise or anti-clockwise. If it is the anti-clockwise, we need to assign the S configuration. If it is the clockwise, we need to assign the R configuration. If it is anti-clockwise, we need to assign the S configuration. If it is clockwise, we need to assign the R configuration. Okay, thank you. Wind up.
Yes. Thank you and one and all.